All right, greetings everyone. Welcome to our first PowerPoint, our first video, I should say, for section 3.3. Now that we have an idea of what derivatives are and what they represent, we're going to start digging in really deep into different ways to find the derivatives of particular functions. Okay. And so section 3.3 is where we start to talk about differentiation rules, which are AKA the shortcuts, and I'll show you what I mean by shortcuts here in a minute. Before that though, just some new notation that you'll need to be aware of as we move forward here. So before in section 3.2, when we were talking about the derivative of a function, we had, if that function was called f of x, we had the derivative, we used that f prime notation. Remember the f with the apostrophe of x, okay? Now another way that we can indicate we're taking the derivative of something is with this notation here, this dx. And what that represents, so the way to think about that is the d on the top stands for like derivative, and then the dx part on the bottom is like with respect to x. So in each of these, they're telling us to take the derivative with respect to x, because that's our variable in each of these cases. So notice we have, for example, in that first one, d dx of 2x squared. If we put that through the limit definition of the derivative, it's 4x. On the second one, if we have d dx of 3x squared plus 3, put that through our limit definition of our derivative, we'll get 6x in this case. Okay, so again, d dx, that means we're talking about derivatives. Okay, so let's talk about then using this notation and finding derivatives of constant functions and power functions. And before we jump into this, I'll tell you that kind of the intent here is to move away from using the limit definition of the derivative to find derivatives. You probably found as you were doing your homework that using that limit definition is quite bulky. And it takes a lot of algebra, and you probably don't want to be doing it every single time you take a derivative. So let's see if there's another way we can come up with for these functions. So we're going to take the derivatives of these four functions here. And as we're doing this, there's some prompting questions there for us. So what do we notice? And can we make any generalizations about the derivatives of constant or power functions? Okay. So let's do this now. And remember, in each of these, we're using that limit definition. So I'm going to write it down and then erase it, but just to remind us. So remember, if we're using the limit definition of the derivative, that's the limit as x approaches h. Sorry, that's wrong. Not as x approaches h. As h approaches 0 of f of x plus h minus f of x all over h. So that's our limit definition of our derivative. So let's apply that to these. So for the first one there, we're finding the derivative of 5, which 5 is a constant function, right? It means that regardless of what we plug into that function, we get 5 as our output. So if we're going to use the limit definition here with the limit as h approaches 0, well, if we plug in x plus h into this function, what do we get as our output? Oh, we see that that would be 5, right? Because regardless of what we put in, we get an output of 5. Minus, well, then we can also put in just x, but we notice again if we do that, we just get 5 as our output, because again it's a constant function. So we end up with 5 minus 5 over h. This will become the limit as h approaches 0 of 0 over h, which 0 over h is just going to give us 0. And so we have the limit as h approaches 0 of 0. But here we're taking the limit of a constant. And you may remember when we take the limit of a constant, it's just that constant. So here we would just get 0. Okay. So the derivative with respect to x of 5, or if our function 5 was f of x, we see that f prime of x is just 0. Now let's think about this. Did this depend on the fact that our outputs were always 5? Could it have been some other number, like if we had 7 or 11 or 42 or negative a billion? Would this have changed at all? The answer is no, right? So what do you suppose that tells us about the derivative of any constant function? right, the derivative of a constant will always be 0. So in this case, we see that this derivative is 0, and that's true of any constant function. All right, let's do x squared then. So here now, we'll do the limit as h approaches 0. I'm going to do f of x plus h. This means we plug in x plus h for x, so x plus h squared minus x squared all over h. And then we start to do some simplifying, some multiply out there on the top. So the limit as h goes to 0 of x squared plus 2xh plus h squared. If I multiply out the top there, the x plus h squared, we have the minus x squared still, and then all over h. Okay. And here, a couple of things cancel. We have this x squared and this minus x squared over here. So those will cancel. So then we'll have the limit as h approaches 0 of 2xh plus h squared all over h. On the top there, we can factor out an h, so we have the limit as h approaches 0 of h times 2x plus h all over h. Here, the h's will cancel. And so our limit then just becomes the limit as h approaches 0, and sorry, that's kind of hard to read, of 2x plus h, and here h is in the domain of this function, so we can just plug in h equals 0, and we'll get 2x there. Okay, so our derivative of x squared is 2x. All right, so I'm going to erase this. I'm doing this on purpose because I want us to see what's going on. Okay, so we have now, again, derivative with respect to x squared is just 2x. Now you guys are lucky that we're doing this on a video, because if we were doing this in class, I would make you do out this next one, but let's set it up. So here we would have the limit as h approaches 0. Now we're plugging in x plus h here, so x plus h cubed minus x cubed all over h. We would need to then multiply out this part, this x plus h cubed, and a little trick for how to do that. So if we're going to do that, we would have, I could break this up into x plus h squared times x plus h, because then it's the x plus h squared times x plus h gives us x plus h to the third. And then we could multiply out that first part. We already know how to do, so we'd have x squared plus 2xh plus h squared, and we'd multiply that by x plus h. And the way you do that is you just kind of distribute everything from the first one into the second one. And as you can see really quickly, this is going to get a little nasty. So I'm going to skip some steps here and just tell you that what we end up with is, at the end of all this, is just 3x squared. Okay. We could use a similar approach for the derivative with respect to x of x to the fourth, which would give us 4x cubed. Now, if you look at each of those, 2x, 3x squared, and 4x cubed, and compare them to their original functions, do you see any relationship there? Well, if I'm going from, say, x cubed to 3x squared, I kind of see, oops, I kind of see that this 3 that's in the front here, that's also in the exponent, so maybe that gets moved down to the front. But then where would the 2 come from? Well, 2 is 1 less than 3, so maybe they're doing something like 3 times x to the 3 minus 1. They would then give us this. Does that work for the other 2? Oh my gosh, I think it does! Okay, so here is our punchline then. So some rules we can use to find derivatives of constant functions and power functions. So first of all, if we have a constant function, so like f of x equals c or something like that, if we take the derivative of that constant, it will always be equal to 0 for any real number. It doesn't matter what it is. And then our power rule for derivatives tells us that if we have a power function like this, we can find the derivative by bringing the power down and then subtracting 1 from it. So as an example of that, if we're doing the derivative of x to the 4th, well, we can do this by bringing the 4 down to the front. So 4 times x, and you subtract 1 from the exponent, 4x cubed, which is what we saw on the previous page. Okay? So isn't this nice? Now, without having to do out that long limit definition of the derivative, we can just do this for constants and power functions. Great. Okay, now one other rule that we need to know, and then we'll use it to find some derivatives, is our constant multiple rule, which basically tells us that if we have a function being multiplied by a constant, and we're trying to find the derivative, what we can do is just take the constant and multiply it by the derivative of that function. So let's look at an example here with this first one. So here we have f of x equals 3x to the 5th. Notice there's a constant out front. So we have that 3 there. So to find the derivative of this, well, all we need to do is take that 3 and multiply it by the derivative of the other function, so x to the 5th. Well, using our power rule, that's going to be, if we bring the 5 down, that'd be 5, and then x to the, and we subtract 1 from the exponent, so we get 5x to the 4th. We can multiply the 3 and the 5, and so we end up with 15x to the 4th is what that's supposed to say there. Okay, so 15x to the 4th would be our derivative of 3x to the 5th. All right, let's look at the next one. So we have g of x equals 1/2 times x squared. So again, we're going to use the constant multiple rule along with our power rule. So we're going to have 1/2 times the derivative of x squared, which we just saw as 2x. And if we do 1/2 times 2, we'll get just 1 times x. So our derivative here turns out to just be x. Okay. All right, what about the next one? So h of x equals -4 root x. Now for this one, we have a constant multiple, but now we have a root. And Cody didn't tell us how to find the derivatives of roots yet. So this problem's probably impossible, and we should just skip it and go on to the next one, right? No, definitely not true. So what are we going to do? Well, could we rewrite square root of x so that it's something raised to a power? And it's more along the lines of what we have been doing. And I think hopefully you're saying yes. The answer is yes. So we can rewrite this as -4 times x to the 1/2 power. So remember, roots you can rewrite as fractional exponents. Then we can take the derivative using our constant multiple and our power rule together. And you know, I've been writing out doing the constant times the exponent, but we can just do that all at once. So if I bring this 1/2 down and multiply it by -4, what do we end up with there? All right, we'll have -2, and then times x to the, and we have to subtract 1 from 1/2, which when we do that, we're actually going to end up with -1/2. So our derivative becomes -2 times x to the -1/2. And we can actually leave our answer like this, or if you want to simplify it a little bit more because you don't like that negative exponent, we can rewrite this as -2 over x to the 1/2 or over the square root of x. Any of those are acceptable. Okay. All right, and then the last one. So j of x equals -2 times x to the fourth. So similar to what we did with the last one, or the previous one. We need to rewrite this as a power function. And it might be tempting to say it already is because you see that fourth power in the denominator. However, it's down in the denominator, which is not what we saw before. So we have to deal with that somehow. So how could we do that? Well, we need to first rewrite this as j of x equals -2. And I want to write that times x to a power, which notice is different from what I have before because here it's -2 times x, here it's -2 divided by x. So it's like I've brought the x out of the denominator, and when I do that, what happens to the exponent? Right, it becomes a -4. Okay, so now we've turned this into -2 times x to the -4. Now we can take our derivative, so if j prime of x, again, use our power rule, so bring down the -4, multiply it by the -2. So this would become +8 times x to the, and we take 1 away from the -4, which gives us -5. We can leave our answer like that, or if you want to write it with a positive exponent, we can write it as 8 over x to the 5th. Okay? Good times, right? Good times. Okay. Let's look at some more with these differentiation rules. So what if we want to find the derivative of a polynomial, which is a sum of power functions like this? So now we have two functions being added together. What do you suppose we might do here? If you're thinking add the derivatives of each function, you would be correct. So one way to do this is to do k prime of x is the derivative of the first thing here, which is just x, which let's think about that for a second. We're going to use our power rule. What is x to a power? Well, that's x to the first. So if we use our derivative rules, it means move this down and then subtract 1 to it. So this would become 1 times x to the 0. But remember, what's x to the 0? That's 1. So this just becomes 1. So if 1 plus, and then we're taking the derivative of x squared, which we just saw is 2x. Okay, so our derivative here, k prime of x, would be 1 plus 2x. All right, so that property or that example we were just looking at was for a polynomial, but it turns out this holds for sums and differences of any two functions. So if we have two functions being added, and actually this could be even more functions, it could be 3, 4, 5 functions, infinite functions, however many. If you add them together, then you can take the derivative by adding their derivatives together. Or if they're being subtracted, you can find the derivatives by subtracting their derivatives. Okay. So that brings us to this slide, which has some more functions on it for us to take the derivatives of. And you guys are going to do the first 3 in a classwork set. But I want to look at this last one together. G of x equals x squared plus 1 over x. Find our derivative here. Now here you'll notice we have a problem where there is a variable in the denominator and a variable in the numerator, right? So it's not like we can just plop the variable out of the numerator, although that is one way you could do this. But what I'm going to do is rewrite this. So I'm going to write this as g of x equals x squared over x plus 1 over x. Now let's think about what I did and is it legal. So it looks like between these two functions, I kept the denominators the same for everything, but I split up the numerator. Now, is that allowed? Oh, gosh. Is that allowed? Well, I think I've talked about this before. If we have two fractions being added together, like 3/4 plus 2/4. We can add those together because they have the same denominator, which would give us 5/4, but that's really the same as 3 plus 2 over 4, right? Remember, equality is something that goes two ways. So if we can go from the left to right to show that 3/4 plus 2/4 equals 3 plus 2 over 4, it should go the same other way and say that 3 plus 2 over 4 should be 3 over 4 plus 2 over 4. And that's essentially what we're doing here. We have this x squared plus 1 over x. We're breaking it apart, so doing kind of the opposite like we did here, to get x squared over x plus 1. Okay? And once we have it like that, then we can start to do some simplifying. So it's become g of x equals x squared over x reduces to x. We still have the plus 1 over x. And now we can take our derivative. So g prime of x equals, well, the derivative of x, which we just saw, is 1. And then how are we going to deal with this 1 over x here? Well, this is another one where we need to rewrite it as a power function. So this would be x to the negative 1 now, if we bring that out of the denominator. And we take our derivative by using our power rule. So bring the power down to the front and then subtract 1. So it becomes minus x to the negative 2, which you can write as 1 minus 1 over x squared. Okay, so sorry, this is kind of sloppy. Let me do this. Final answer would be g prime of x equals 1, what did I say, minus 1 over x squared. Yeah. Okay. All right, that's all I got for you now. Thank you for watching.